Hello, everyone. Today we're going to unravel a really fundamental concept in physics, something that totally changed how we think about motion, and it actually started way before Einstein. We're talking about classical relativity, and it all kicks off with a simple question about, well, your point of view.
Okay, so let's jump right in with a classic puzzle, one that Galileo himself thought about. Picture this: a ship is sailing smoothly across the ocean. A sailor is way up at the top of the mast and, whoops, drops their binoculars. So the big question is, where are they going to land on the deck?
Now, your gut might tell you one of two things, right? Does the ship just sail out from under the falling binoculars, meaning they land somewhere behind the mast? Or do they somehow fall straight down and land right at the base? Take a second, think about it. One of these probably feels more intuitive, but the real answer is, well, it's pretty amazing.
So to get to the bottom of this, we've got to realize that the solution isn't just about gravity. The absolute key here is that the answer completely depends on who is watching.
And this brings us to the core idea that unlocks this whole puzzle, the concept of frames of reference. You see, everything we call motion is always measured from a specific point of view.
So, when we talk about speed, we're always talking about relative velocity. Think about it. Is a car moving at 60 miles per hour relative to the road? Or is it moving at 0 miles per hour relative to you, the passenger inside? There's really no such thing as an absolute still or an absolute moving. It's all relative.
In that perspective, that point of view, that's what physicists call a reference frame. It's basically the background you're using to measure movement. So, are you standing on the ground? Or are you inside the moving car? Your reference frame completely changes what you observe.
Okay, here's a fantastic way to see this in action. Let's imagine you're in a boat, and you're trying to row straight across a river while the water itself is flowing downstream.
Now, what's so cool here is how we can split this into two totally different viewpoints. If your reference frame is the river itself, it looks like the boat is just moving straight ahead, from one bank to the other. But for someone watching from the shore, they see the boat's forward motion and the river's sideways motion. The two add up, and the boat ends up traveling along a diagonal path.
So this all leads to a really simple and, honestly, an elegant rule. We can figure out what's actually happening by just adding these different velocities together.
So the crucial point is that what a stationary observer sees is the sum total of all the motions happening. You've got the boat trying to push itself across the river, you've got the river itself carrying the boat downstream, and both of those combine into that single diagonal movement that you see from the shore. It's that simple.
All right, so now that we've got these tools, the idea of reference frames and adding velocities, we can go back to our ship and finally, definitively solve Galileo's puzzle. First up, let's put ourselves in the sailor's shoes, on the moving ship. From his point of view, he, the ship, the mast, and the binoculars are all moving forward together as one unit. So to him, the binoculars have zero forward motion. From his perspective, it's exactly as if the ship were tied up at the dock, not moving at all. He just lets go, and he sees the binoculars obey gravity and fall in a perfectly straight line right down the mast. Simple. But now for the fun part. What about someone watching from the shore? Their reference frame is totally different. It's fixed to the land. What do they see?
Okay, so from the shore, the binoculars already have all of the ship's forward speed the moment they're dropped. So as gravity pulls them down, they're also still traveling forward. And when you combine that steady forward motion with a downward fall, what do you get? A perfect curved arc, a parabola. And this, right here, is the absolute beauty of classical relativity. One observer sees a straight line, the other sees a curve. They see completely different paths, but they both see the exact same result. The binoculars land right at the base of the mast. The laws of physics work perfectly in both reference frames. They're both right.
Now, this isn't just some old-timey thought experiment about ships. This exact same principle is at work all around us, every single day, just at much higher speeds. Let's bring this idea into the modern world.
Imagine you're on a commercial airplane, just rocketing through the sky at a blistering 260 meters per second. That's incredibly fast. Now, what happens if you just drop a coin in the aisle?
It's the exact same story as the ship, just way faster. To you, the passenger, your reference frame is the plane. You and the coin are in the same moving bubble, so it has zero horizontal speed relative to you. It just looks like it falls straight down to your feet. But for someone watching on the ground, whoa! They see a coin that was already fired forward at 260 meters per second, which then starts to fall.
It would trace this huge, long, graceful arc through the sky.
And here's the most important part. Even though what they see looks totally different, they both agree on the fundamental physics. They would both agree that the coin fell a vertical distance of 1.5 meters. They'd both agree it landed right below where it was dropped relative to the plane. The laws of gravity work perfectly for both of them.
So this whole idea, this principle, that the laws of physics are the same for everybody who's in constant steady motion, that's what we call classical relativity. It's the rule book for how motion works in our everyday world, from walking down the street to flying across the planet.
But, and there's always a but in physics, isn't there? This beautiful, elegant system has its limits. It works perfectly for ships and planes and pretty much everything we experience, but it starts to break down when you get really, really fast, like close to the speed of light fast. And asking that question, what happens then? Well, that's what sets the stage for a young Albert Einstein to revolutionize physics all